Good day, I'm Maile Matsiba. Welcome back to our channel. We continue with class test 1 of 2011 and we're looking at part 5, which is question number 2 and question 2b. So let me just go through yet again the information that has been given here. It says the table shows the solubility data of sodium carbonate in water, and that's the table, and it even says that interpolate linearly if required. It says a raw material contains 80% Na2CO3 10H2O and 20% inert solids which are insoluble. Now it says the raw material is dissolved in fresh water to give a saturated solution at 17 degrees Celsius. This solution is passed through a filter to remove the inert solids as a wet filter cake, and the clear solid from the filter is treated with phosphoric acid A3PO4 to produce disodium hydrogen phosphate according to the chemical reaction equation. Now it says the phosphoric acid is charged to the reactor as a 40% solution of H3PO4. This is the 40% solution of H3PO4 in water. It says the charge is stoichiometrically correct. The CO2 is removed from the reactor as a gas. Here is it. And the reaction goes to completion. And also the product stream contains only dissolved Na2HPO4. Now, when you look at this, it's important. Now we go in question 2b. It's very much important to notice two elements or two important facts here. They say the charge is stoichiometrically correct, which means the amount of H3PO4 that has been charged, it matches or it's equal to the amount required to react Na2CO3 that has been charged. And it also says that the chemical reaction goes to completion. So those two elements are very much important as we're going to be looking at 2b. Now let me just go to the question. It says use 100 kilograms per hour of the Na2CO3 solution as a basis to calculate the following. The phosphoric acid H3PO4 solution flow rate in kilograms per hour. They say use 100 kilograms per hour of this solution as a basis to calculate the total solution of H3PO4 in water. So we need this total solution, but we're going to use 100 kilograms per hour of this solution. And remember, they are saying that this charge or this solution is actually stoichiometrically correct, and this reaction, which is here, goes to completion. Now I have a couple of steps, 5 steps. So the very first step, let me just write it down. Step 1. The very first step that we need is to calculate the mass of Na2CO3 in the 100 kilograms per hour solution. Remember, we are told that we are using 100 kilograms per hour of the Na2CO3 solution. This solution weighs Na2CO3 and water. So now the important question is that out of this 100 kilograms per hour solution of Na2CO3 and water, how much Na2CO3 is there? What is the mass of the Na2CO3 in this solution? And that is actually our very first question or our very first step. So let me just write it down that calculate the mass flow rate. Calculate the mass flow rate of Na2CO3 in the 100 kilograms per hour Na2CO3 solution. So that is actually the question. And for us to go about that, it's important. Let me just highlight something here. For us to go about that, let me just also write the basis. Though we are given, it's always important to write it. Basis is 100 kilograms per hour of Na2 or saturated. This is important. Saturated Na2CO3 solution. Right? So that is actually our basis. Now, when we answer the question as to how much is the mass flow rate, we know very much that the mass flow rate, let me just write the equation here. The mass flow rate of Na2CO3 is equals to, remember, if we have the total solution, for us to get the mass of Na2CO3, we only need the mass fraction of Na2CO3 in this solution. And remember, this is actually the saturated solution. And in the previous equation, we did calculate the mass fraction of Na2CO3 in the saturated solution. And we found that mass fraction to be 0.15825. So let me just write down here that the mass flow rate of Na2CO3 is equal to the mass fraction. Let me just add an additional step. Mass fraction of Na2CO3 multiplied by total flow rate of solution. I hope it's clearly visible. So the mass flow rate of Na2CO3 is the mass fraction of Na2CO3 multiplied by the total flow rate, which means it's actually the mass fraction of Na2CO3 multiplied by the total solution here. And if you do that, we know that the mass fraction we calculated in the previous questions to be 0.15825 multiplied by the total flow rate. We have been given that we need to use 100 kilograms per hour. So it's 100 kilograms per hour, and if you use your calculator, it gives you 15.825 kilograms per hour. Now, with this said, we know for sure that in this 100 kilograms per hour of the solution of Na2CO3, there's actually 15.825 kilograms per hour of Na2CO3. So that is the first step. Now, this takes us to our step 2. Now remember that the actual question here, they want to know about the phosphoric acid, the charge here, the total solution here. And we know that we don't know much about the H2SO4 except the percentages, but we know that the Na2CO3 actually reacts with the H3PO4 according to this reaction equation. So they relate, because of the equation, they relate on a mole basis. So an important step to do is to calculate the number of moles of the Na2CO3 so that we can be able to relate it with the H3PO4. So our step 2 is now calculating the molar flow rate. Let me just write it down, that calculate the molar flow rate of Na2CO3, right, in the saturated solution. It's also important to notice that because now that we know the Na2CO3 here in it, we don't really need to worry much about the water, because remember, the equation doesn't really include the water in the reaction here. So we now going to be focusing on the Na2CO3, and that's exactly what we're going to do that. So with that said, we can just say number of moles of Na2CO3 is equals to, we know that the number of moles of Na2CO3 is going to be the mass over the molar mass. So it's going to be mass flow rate of Na2CO3 all over molar mass of Na2CO3, right? And it's equals to, we know the mass flow rate to be 15.8, so it's 15.825 kilograms per hour all over. We know the molar mass of Na2CO3, it's 106 kilograms per kilomole. So our answer becomes, when you use your calculator, is 0.14929 kilomole per hour. Now, this is the thing. We know that the Na2CO3 that is charged to the reactor is actually 0.14929 kilomole per hour, right? And we are told that the H3PO4 charge is actually stoichiometrically correct, which means the number of moles of H3PO4 charged into the reactor are exactly the number of moles required to react the Na2CO3. And with that said, when we look at the equation, which is very much balanced, we learn that the ratio of Na2CO3 and H3PO4 It's actually 1:1. Now that tells us that takes us to our step 3. Now in step 3, we're going to calculate the mole flow rate of H3PO4 in the solution. And we're going to be using the equation, the reaction equation, and also the Na2CO3. So let me just write it down, that calculate the molar flow rate of of H3PO4 in the H3PO4 solution. Right, that is our step. And going about that, it shouldn't be so difficult. We can just write that the ratio, let me write it down, the ratio of Na2CO3 and H3PO4 is 1:1. Therefore, the mole flow rate, the molar flow rate of H3PO4 is equals to 0.14929 kilomole per hour. So that is actually our third step, and yeah, that is it. So now that we know that the mole flow rate of NH, now that we know the mole flow rate of H3PO4, we can actually then use this mole flow rate to calculate the mass flow rate of H3PO4, and that is actually our step 4. Let me just write it down here, that step 4 calculate the mass flow rate of H3PO4 in the H3PO4 solution. Right? So with that said, if we're going to be calculating the molar flow rate or the mass flow rate, we're just going to be saying flow rate of H3PO4 is equals to, let's see, how do I put it? Yeah, it's equals to number of moles of H3PO4 multiplied by the molar mass of H3PO4, right? Is equals to, we know that the number of moles of H3PO4, we have calculated those number of moles to be 0.14929. So it's equals to 0.14929 kilomole per hour multiplied by the molar mass of H3PO4 is 98 kilograms per kilomole. Now if you use your calculator, it gives you 14.63042 kilograms per hour of H3PO4. Right? Now that is actually our step 3. Now that we know, remember, we need to calculate this flow rate. Now that we know the mass fraction, the mass flow rate of H3PO4 and the percentage, we can actually go to our step 5, which is calculate the mass flow rate of the H3PO4 solution. Right? And for us to be able to get that, it's always easy. Yeah, all right. Yeah, there. Yeah, I think it's visible now. So for make it easy, let's just say let X be the flow rate of the H3PO4 solution, right? So we're defining that solution as X. Then we can just say, therefore, 0.4x is equals to 14.63042 kilograms per hour. Therefore, x is equals to 36.6 kilograms per hour. So that becomes our final answer. Remember, what we actually did here was that because we know that this is 40%, then we defined the whole thing as x and used that 40% and also the mass flow rate of H3PO4 to actually get that x. So thank you for your time, and I hope we meet again in our next video.